how would that work? Well, you have two different kinds of architectures. You could have a procedure, which we will call proc for the moment, which so you have two different things. One is if you give it ahead of time, they could write a procedure that just takes x and returns, which we will write like this. Procedure applied to x will compute x squared minus 1. Right? That's one possible design. But another design would be that they write a procedure that somehow I'll put it in quotation marks like a string, but it's not a string. Okay, it's something so if it's not a string, I shouldn't put it like a string, but there's no good notation in C, right, to talk about this, but so I'm going to put double quotation marks, right? So whatever comes in the double quotation marks, forget about C for a moment. It's something that represents what's inside, right? So the procedure will take in a description of x squared minus 1. So x squared minus 1 is actually pretty easy to represent. Okay, we can think about that, but you can write it with just bits in the computer, and there isn't that much that you need to specify because it's a tiny thing. So you have the description and then some value of x, and then that will produce the result. So you give the expression. This is going to be called the expression. I'm not saying how you represent it. All right, there are tons of different ways of writing functions down, depending on the kind of functions you want to be able to represent, and so on. And the procedure will have to know about the convention you used to represent functions. So to simplify your life, you better make sure that everything makes sense to you. And then there's this actual value, right? 3.5. And then the computer will give you the result of applying this function that corresponds to this expression to 3.5, right? So expression, value, result. You could, whereas here you yourself, right, wrote a program that takes a value and gives you a result. There's this hybrid way, which if you don't care at all about performance, it's pretty similar, but instead of writing a procedure that has to, for every value, it has to sort of parse the expression, right? If I give you 3, then 3.1, 3.2, 3.3, you're still going to do the same work of figuring out that, this thing means x times x, and this thing means minus 1. So this thing means x times x minus 1. This work is still going to happen every time. But it's possible to just do that work once, and then so what you produce is an actual function. So then you would say like this, right? And what it produces is a second procedure which takes an x, and that second procedure returns x squared minus 1. So you have a procedure that makes a procedure, or at least it makes something where the work of parsing has been done. One simple way of doing that is just writes it out. It spits out a source file right? It spits out code, and then the compiler will turn that into binary. If you wanted to get really fancy, you could spit out binary directly, but I'm not sure how often that would be useful. But the basic idea is that this is something you do yourself every time, basically. This is something that happens dynamically. The work of both parsing the expression and applying it to a value gets done every time. And then here, if you want to compile afterwards, get a fast function, this has to happen before the program is run. So in a certain sense, this is just the computer doing your job for this part, right? It's a computer writing the procedure that will give you the correct result. Okay, that's one way to represent functions, and it's pretty useful in many contexts. Polynomials are a pretty limited way of doing that. So what would that look like? So we wrote about polynomials. We implemented polynomials. What does that mean? It means that we have a way in the program to describe this thing. All right, it's going to be a p where p dot coefs is I'm just going to write it like this, even though you can't write that in C. It's the first element is -1, the second element is 0, and the third element is 1. That's a polynomial of degree 2, so 2. Then p is the thing that would go there. Okay. And right now we have this approach. So this approach is exactly what is done when we call evaluate, right? Evaluate poly at. That's what happens. And this is, so you see, representation and then value. I'm going to use these words until you basically get the meaning, and then later maybe I'll try to explain exactly what I mean. But for now, when you hear representation value, just look at where I use the words and try to figure it out, and you'll eventually get it, I'm sure. It's not anything fancy, okay? It's just a way of, you know, representation is a way to represent things, and values is the value of x, like 3.5. If you don't know what I mean right now, that's not helping. If you're not sure that you know what I mean, but you understand that, you know what I mean. So evaluate poly at is an example of doing this kind of stuff for polynomials. That's how we do it. We could, however, spit out a program. That would be, I mean, there are several ways of doing this. In C you have a macro system, which means that there's kind of already ways of doing this directly, which are kind of ugly, but, and more importantly, don't really do exactly what you want. But you could say define P, so para, you actually, I think you need them to be in capital letters, and then A, B, C, D, and A, B, C, X. Okay. And that you write it simply A times X plus B times X plus C. And then whenever you'd like to have whenever you would feel the need to hard code the coefficients in a polynomial so that your code run faster, you can just write this. That's exactly what it's going to do. Before it compiles, it's going to replace that with that. Pretty simple. And it's not really what we would want. We would want something that could just make on demand a piece of code. This is with the macros used in this way. It's a bit like this, but now the representation is hand coded. You can't have another part of your program decide what the coefficients should be, right? Let's leave that alone for now. I could go on, but it would it would be pretty abstract before we actually use any of this. Okay, so another thing you can do is you can approximate the function. So you can lose information. One way to do that is to just fit the best polynomial to one specific function, right? And then you can write the function as a polynomial. We've already seen how to do that. Once we have the polynomial, we've seen how to deal with the polynomial. But to get the polynomial, you can just approximate the function, say, what's the best polynomial of degree 10 that fits my function? How do you do that? So you can find whatever method you like. And then you have a polynomial instead of the function you had at the beginning. For example, a Taylor expansion, and forgetting some terms, gives you a local approximation, an approximation that's supposed to be good around one particular point. You could also imagine a global approximation that tries to find the best polynomial that reduces the overall distance over a wide interval between the approximation and the actual function. Another way of doing it is to take sample your function at a few points. So you've got x equals to 0, 0.5, 1, etc. They don't all have to be at the same distance from each other, but